Hello, chemistry people. I hope you are doing well and you've been getting outside at least a little bit. Now you've had a couple days to digest the big news from College Board, and you understand that when you take the AP exam now, you are only going to be responsible for the information presented in Units 1 through Unit 7. Now, even though we moved on from Unit 7, Equilibrium, there's actually a couple topics that we did not discuss. And the reason I decided to table those is because I figured that would make more sense once we got a little bit more background knowledge about entropy, for example, or in this case, pH. So the purpose of this video is to talk a little bit about the relationship between solubility and pH. So we're going to talk back again about KSP, and we're going to combine that with your understanding of weak acids and bases, all right? So let's begin. So I believe that you completed some ChemQuest worksheets about salts, and you understand that salts are created during neutralization reactions, and those salts can be acidic, basic, or neutral. And up here I have examples, 3 examples, one of an acidic salt, one of a neutral salt, and the third one of a basic salt, right? And those are created under different conditions which are described. Now, we know that the dissolution of a salt is a reversible process, and that dissolution will be affected by environmental factors. For example, we learned about the common ion effect, and if there's the presence of an ion that's in common with the salt, well, then that will reduce the solubility of that salt. Well, pH also has an effect, so it's important to understand the acidic or basic nature of these salts. Now, we can understand this quantitatively, which we'll look at briefly, but it's even more important that you can be able to explain any of these trends or these phenomena qualitatively using Le Chatelier's principle, right? So here is the first example that I have for you of magnesium hydroxide. Magnesium hydroxide dissolving has a solubility product constant of 1.8 times 10 to the negative 11th. And in a saturated solution, magnesium hydroxide will have a pH of 10.52. So this is going to be a basic solution. And we can do some calculations and we can figure out the concentration of magnesium ions, and we'll get like 1.7 times 10 to the negative 4 moles per liter, the capital M again being molarity, right? All right, well, let's suppose that we put the solid magnesium hydroxide in a buffer. Now, you started learning a little bit about a buffer, and a buffer is really just a solution that if you add relatively small amounts of an acid or base, the pH is going to remain relatively stable, right? So here we have this magnesium hydroxide in a solution that's buffered to have about a pH of 9. Now you understand the relationship between pH and pOH at this point, that they have to sum up to 14. So if we have a pH of 9, the pOH has to be 5. And because you understand the definition of pOH being the negative log of the concentration of hydrogen, or rather hydroxide ions, you know you can calculate that the concentration of hydroxide ions in the solution will be 1 times 10 to the negative 5th. Now, if we plug those values into the solubility product expression, we can then find that the concentration of magnesium ions will be 0.18 moles per liter. Now, compared to our saturated solution that had a pH of 10.52, we can look at these values and see that if we have a lower pH, right, then we're going to get a lot more of this salt dissolve. Now, remember that pH is a logarithmic scale, right? So the difference between one value and another is actually 10 times more and not just one more, right? So we can see that this is a really drastic effect. Now, well, what does this mean? Let's talk about this another way. If we decrease the concentration of hydroxide ions by making the solution more acidic, right? We're going to add more protons, more hydrogen ions. Then the concentration of magnesium ions would increase to maintain that equilibrium condition. So if we add enough acid, right, then that means if we had a sample of magnesium hydroxide, we could get it to dissolve completely, right? So the solubility of almost any ionic compound can be affected if we change the solution's concentrations of hydrogen ions and hydroxide ions, if we make it more acidic or more basic. Now, you should know that these effects really are typically only noticeable when one or both of the ions that are involved are at least moderately acidic or basic. Now, our previous example right here with magnesium hydroxide is a metal hydroxide, and that is a compound that acts as a base, right? It's a strongly basic ion, the hydroxide ion. So we will see that noticeable effect. Now, there is one more example here with calcium fluoride. And calcium fluoride solubility curve we can see over on the right, and we can see there that if we decrease the pH, that is, if we increase the hydrogen ion concentration, then the molar solubility of calcium fluoride will increase, right? And remember that we're talking about different orders of magnitude. If we're looking at the units on the y-axis there, we can see that we're looking at the order of 10 to the negative third. So it's a pretty drastic increase. Why does this happen? Well, this happens because fluoride is a weak base, right? So we can shift the solubility of calcium fluoride right just by protonating this fluoride anion. And you can see the overall process represented in the equation just below. So this leads us to some general rules, right? So general rule number one is that the solubility of slightly soluble salts that have basic anions, that solubility will increase as you increase the concentration of protons, right? That is, if you decrease the pH. On the flip side of that, if we have slightly soluble salts that have acidic cations, we can increase that solubility if we increase the concentration of hydroxide ions. That is, if we decrease the pH. And if we have salts that have ions of negligible acidity or basicity, well, it's not really going to be that affected by the pH changes that are experienced. So what I'd like you to do is try to put this all together and answer a practice problem. So which of the following substances will be more soluble in an acidic solution than in a basic solution? So why don't you pause the video here, try to answer this, and I'll give you a hint. Look at the ions that compose each of these salts, all right? And then ask yourself, if it's in an acidic solution, will more of it dissolve, all right? So pause the video, answer the questions, and then we'll discuss the solutions. So for our first substance, our first species, we're looking at nickel hydroxide. Nickel hydroxide actually will be more soluble in an acidic solution, and maybe you were able to identify this because you noticed that hydroxide ion. The hydroxide ion will interact with the protons being donated by the acid to form water, and as a consequence, this reaction, this process will shift right, causing more product to form and more of the nickel hydroxide salt to dissolve. All right, let's go on to the second substance. So our second substance was calcium carbonate, and you may or may not have been able to recognize that carbonate ion is a basic anion, and it will react with the protons from the acid. Now this situation is a little more complex. As you can see, now we have an additional reaction we're going to consider. So the first one is similar to the last. We're looking at the dissolution of the salt into its constituent ions. Well, the second one is also similar, except instead of the hydroxide ion, we have that carbonate ion interacting with the protons from the acid to form carbonic acid. The carbonic acid then will break apart into carbon dioxide gas and water. So if we look at the overall reaction, if we're adding an acid, the protons from that acid will react with the carbonate ion to form water, and as a consequence, that reaction will shift right towards more products, and we will get more calcium carbonate being formed. All right, let's move on to part C of this problem and the substance involved there. All right, this one has barium sulfate, and this one was a little bit trickier, right? Sulfate is a rather relatively weak base, and it's not going to interact that much with the protons from the acid. Consequently, it's not going to be affected that much. However, because it still will react with the proton, If we have a really strong acidic solution, then we should get more of this dissolving. Now, will you have to make the distinction here? Probably not. And you still recognize that, okay, if we make it strong enough, then we're going to get more dissolved. But the fact that sulfate ion is rather weak means the pH change really isn't going to have much of an effect on the solubility. All right, so let's do part D. So we're considering part D now, and we're looking at silver chloride. Well, chloride anion is the anion of a strong acid, hydrochloric acid, and consequently is going to have basicity that's really negligible. It's not really going to interact much with the proton. So as an effect, that pH change really isn't going to have much effect on the solubility of this salt. So hopefully this video helped you to understand a little bit more about the relationship between the solubility of the salt and the pH of the environment in which that salt is. If you do have any questions, remember we have this community board that you can post questions to, and hopefully some of you are looking at that and answering each other's questions. You can also bring up your questions at our next Zoom meeting, where I look forward to seeing all of your faces again. All right, so enjoy the rest of your day, and hopefully I will see you soon. Stay well.